So thank you very much for this invitation. I will talk about a joint work with Vladimir Lazić. So I'll start with an introduction. Of all the objects. In this talk, we'll have X and Z, projective, normal, and complex varieties. But more than in varieties, I'm interested in pairs. So I'll just briefly recall you what a pair is. It's the data of a variety and a Val divisor. So it will be with rational coefficients for us today. And together they have the property that Kx plus B is Q Cartier. Okay, if you're used to pairs, maybe you can notice that here I'm not assuming that B is effective. Okay. And the objects I study are called KLT or LC trivial fibrations. So this is the notation, F from XB to Z. They are the data of a pair. A fibration. So F is a connected morphism, is a surjective morphism with connected fibers. And so the crucial condition is this one. There exists a Q Cartier divisor D on Z such that Kx plus B is the pullback of D. And then there are some technical conditions. We assume XB to be respectively KLT or LC. So LC has already been defined, but let me just recall that. So KLT for Kawamata log terminal and LC for log-canonical are regularity conditions. And they are regularity conditions that can be checked on the coefficients of B on a suitable birational model of X. And let's say that if X is smooth and B is simple normal crossing, then they become, so LC. So we write B as the composition of its irreducible summons. And LC becomes BI at most 1 for all I, and KLT. So we have the same inequality, but strict. Okay, and then we have another condition, which I will not tell. So it's a...
You're calling KLT what is usually sub-KLT.
Yes, because my pairs are what is usually called sub-pairs. Okay. So I'm just throwing the sub away. Yes. Yeah, and then we have this other technical condition. I will not tell you what it is, but I'll tell you what it does. It makes B behave almost as an effective divisor. So B is almost effective. So 4 and 5 are technical conditions. What makes these fibrations special is condition 3. So for instance, if B is equal to 0, and if you restrict to a general fiber, you can see that a general fiber has trivial canonical. So this is a restriction on the geometry of the fibration and of X. Okay, maybe some examples. So the first example I want to give you is the one of relatively minimal elliptic fibrations. So what does it mean? It means that X is a surface, a smooth surface, and C is a smooth curve, and the general fiber is an elliptic curve. So this is an elliptic fibration, and relatively minimal means just right here. Relatively minimal means that there are no -1 curves inside the fibers. So if F is a relatively minimal elliptic fibration, then F from x, 0 to C is a KLT trivial fibration. Okay, the second example. For the second example, we're going to take X, P1 cross P1, and we take D, a divisor of B degree, let's say dk on X, and then the second projection, so from X and then I take as boundary 2 over d 2p1. Maybe d reduced. And I want also maybe d at least 2. So the second projection is an LC trivial fibration. So these two examples show two very different situations. The first one where the fiber vary, maybe the fibers are not all isomorphic, and then the second situation where the fiber doesn't vary at all, so it's a product, but the interesting geometry is given by the boundaries, so the points that move in the fiber. Okay, maybe I can convince you that this is a KLT trivial fibration. This kx plus 2d has b degree, so the canonical, it's -2, -2. And then d, it's dk multiplied by 2 over d, so it's 0 and -2 plus. Okay, so it's a pullback from the base. Okay, so now we consider an LC trivial fibration, and we define an object called the discriminant. So it's defined by a formula. Let me write the formula and then I'll tell you what it is. So it's a sum over the irreducible and reduced subvarieties of codimension 1 of z of some coefficients 1 minus gamma p times p. And now gamma p is again defined by a formula. So we take the soup over all the non-negative real numbers such that this pair is LC over the generic point of P. Okay, so what is this? So LC, we've already said that it's a regularity condition. Let's say, for simplicity, the coefficients of delta B plus T times the pullback of P. Let me write delta as sum of di delta I. Okay, and then over the generic point of P, means that I check this condition only on the di such that the delta I surjects exactly onto P. Okay. So maybe this is not super clear yet. Okay. No. But I'll just tell you some properties first. So facts. BZ is a Q-vile divisor. So this means that the sum is finite. And the gamma p's are rational numbers. And then there is another important property proved by Ambro, saying that if kz plus bz is Q Cartier, and the B in the boundary is effective, then the singularities of B, so are appear exactly in the singularity of the pair Z BZ. So this is a manifestation of the inversion of adjunction, which has been already mentioned. And then maybe I want to say 2 words on actually what is this. What is this BZ? So if you don't like the formula, what does it mean? So let's say that gamma p equals 1. So gamma p equals 1 means that this pair, x plus the pullback of p, has the regularity condition log-canonical. So it is regular. In the category of regularity that we have chosen. And if gamma p is less than 1, then the same pair is, let's say, does not have this regularity condition, then it's more singular. So we can look at this support of VZ. So this is the union of all these dimension 1 subvarieties, such that this pair is singular. So it's a sort of singular locus of F, but seen from a pair to a variety. So this discriminant detects the singularities of F. Okay. Okay, and now I can introduce another object called the moduli part. This is defined as D minus KZ minus BZ, where let me recall that D is the one from the definition, which is still on the board. It's this guy.
You have defined the codimension 2.
No. No, this is a good point. Yeah, just the divisorial part. But in a second, I will tell you a result which says that maybe under some special condition, at some point it says everything. And actually, you already have the right condition on the board. Okay. So before telling you the properties of M, I would like to do a small construction. Let's say that we have here so F an SC trivial fibration, and we consider a birational map. Then we can take the singularization of the fiber product, and it comes with two natural maps. We call them F prime and top. And then I want to define a boundary on X prime just by setting this equality to be true. So with this boundary, F prime is an LC trivial fibration. And therefore, it has a discriminant and a moduli part. And this will be, so when I take a base change, these two implicitly denote discriminant and moduli part of the fibration obtained with the base change. So what makes the moduli part special is the following result. It has been proved in different extent of generality by many people. So Ambro, Kawamata, Collar, and Fugino and Gonghio. So we consider an SC trivial fibration then we can find a birational map such that first KZ plus BZ is Q Cartier, or equivalently M is MZ is NF, and every time I take another base change, the moduli part, so MZ prime is NF, and here KZ prime plus BZ prime. For every other birational map, the moduli part I obtain is just a pullback of MZ prime. So on Z prime, all the properties of M appear. So we say that the canonical bundle formula of F is a way of writing Kx plus B as the pullback of the sum of three divisors. So the discriminant, which detects the singularities, the canonical bundle, and the moduli part, which enjoys these positivity properties. But, so maybe more than that, this moduli part is supposed to detect the properties of the fibers in moduli. So whether the fibers vary or not, if they are all, maybe all isomorphic or not. And let me give you the first example of canonical bundle formula for elliptic fibrations. So if F is an elliptic fibration, then there is a theorem by Kodaira and Bueno, maybe like this, saying that 12 times the moduli part is the pullback of a divisor of degree 1 on P1, where J is the J invariant. So this motivates at least the name. If all the fibers of the elliptic fibrations are isomorphic, this map is constant, and therefore MC is trivial. Otherwise, it's ample. Okay. And then maybe another important motivation, another result by Ambro. If donc F is a KLT trivial fibration and MZ is torsion, then X is a product and F is a projection. Maybe modulo a finite base change. Oh, sorry. So the main conjecture about the moduli part states that a similar property is true all the time. It has been stated by Prokhorov and Shupurov. So consider a KLT or maybe LC trivial fibration and then we should be able to find a birational map, rho, and a natural number such that m times mz prime, so mz prime is the moduli part on the base change, is base point free. And maybe for later I will add that I will denote the dependence on K with the conjecture is just for basis of dimension K. Okay. No? In the triviality theorem? Yeah. Yes, there is, but it's KLT. It's not true for LC. So this conjecture is wide open, is probably very hard. It has been proved in some special cases. The conjecture has been proved. Let's say if the fibers have dimension 1, so by Kodaira-Ueno, and by Prokhorov and Shukurov. And for, well, if the fibers have dimension 2 but are not P2, this is by Fugino, and there are some results by Filippazzi. And if the fibers are abelian varieties, let's see, again, by Fugino. Now, some of these results, so everything apart from some of the two-dimensional fiber cases, use the existence of some moduli spaces for the fibers. And there is another result, which is when MZ is numerically 0. So I just remind that MZ numerically 0 means that MZ has 0 intersection with every curve in Z. And so this is a result by Ambro for KLT, and I proved it for LC. So if MZ is numerically 0, then it is a torsion divisor. An immediate corollary of this result is that the conjecture is true when the base has dimension 1. Okay. Now I've given all the important definition and some of the results. And then I can state what we proved with Vladimir Lazić. So I'll state the theorem in two parts. The first one is that it is enough to prove the conjecture when the moduli part is big. So divisor is big if it's the sum of an ample and an effective divisor. And the second part so we assume the conjecture in dimension k-1, and then for all subvariety of Z of codimension 1, we can prove that the restriction, I didn't tell you, is B-semiample. So what does B-semiample mean? So these two lines are called B-semiample. And B stands for birational, and the existence of M such that this multiple of MZ prime is base point free is the semiampleness.
Is it is supposed to hold for every Ambro model.
Yeah, yeah.
Just the sum.
Yeah, no, you're right. So we can say that Z prime dominates an Ambro model, or one can also prove that, well, let's say, and Z prime is as in the theorem by Ambro, Kawamata, Collar, and Fujinagombyo. Yes, it's important that the semiampleness is proved not on any model, but on the one where all the important information is. Thank you. Yes. No. Okay. So I would like to say something about motivation. So the first type of motivation I would like to give is more technical with respect to the result. So as a corollary, maybe of the methods more than of the result, we obtain the following. So we assume the conjecture in dimension -2. Well, now it's far away, but I didn't write it. But in the statement, I'm assuming that the base of my LC trivial fibration has dimension k. I apologize. I hope it's clear from the context that so T has dimension k-1. And so here we assume that the conjecture for basis of dimension k-2, and then we have F with dimension of Z equal to k. And then I assume that MZ is B, and the support of the discriminant with the augmented base locus of MZ, I'll tell you in a second what it is simple normal crossing. Then for every component of this dimension 1 locus, the restriction of MZ is semiample. So just a reminder, the B plus of a big divisor is, so it is the locus where MZ is not ample. and it can be defined as the intersection of all the supports of the effective divisors, such that mz can be written as the sum of an ample plus that effective. And this guy contains the base locus of mz. The base locus is the locus where mz is not semiample. So this result can be seen as an exploration of the base locus of mz, the behavior of the moduli part along the base locus. Okay, so this is the first motivation, but maybe more importantly, so these may be motivation to study the conjecture more than this exact result. So if we have a pair, the object canonically attached to it is kx plus b. And if we want to study the pair, we try to take this object and squeeze as much information as we can from it. So the first thing to do is look at the global sections and its multiples. And so if we take all the spaces of global sections, then they form a ring called the canonical ring. And now, and one of the most important questions, is about finite generation of this canonical ring. So finite generation has been proved in a famous paper by Birka, Cascini, Haken, and McKernan in the KLT case. So, first of all, question is R of xb finitely generated? And so some important answers have been given by Birka, Cascini, Haken, and McKernan. If xb is KLT and k plus v is big, so then yes. And using this result, so there is a theorem by Fujino and Mori. So again, if xv is KLT, then same conclusion holds. And in this theorem, the authors use the result by Birka, Cascini, Haken, and McKernan, and the canonical bundle formula. But it turns out, for a lot of difficult questions, the LC case is very important. And in order to try to reproduce their strategy in the LC case, this conjecture could be really useful. So this is a reason for the importance of the B-Semiampleness conjecture. So I've got 15 minutes for you. Okay. So now I have a bit of time left. I can give you some ideas from the proof. So we will just, let's say, treat a baby case. I will assume that mz is big, and that the dimension of z is 2. And there is a theorem by, and I also assume that z is this z prime. It's a model where mz is an f, and for whatever other birational map, I just obtain the pullback every time. There is a theorem by Nakamaye that says that the B plus, that implies that the B plus of mz is the union of all the curves which have 0 intersection with mz. So I will prove, I will tell you how to prove our result for a component of the B plus in dimension 2 for mz big. And I'll also assume that so just recall that we have f from x comma b to z. I will also assume that the preimage of t, which I'll call xt, is smooth. This is, of course, it's not always true, but at least it will make the proof a little easier to follow. So we write our canonical bundle formula for f. And then I can add xt on the right side and on the left side. And I use the adjunction formula. And we obtain that kxt plus the restriction of b to xt is the pullback of kt plus, well, the restriction of the divisors. So in particular, this proves that the restriction is an SC trivial fibration. So it has a canonical bundle formula. We write the canonical bundle formula, and maybe the discriminant and the moduli part are different. Maybe I won't. Oh, sure. You're right. I'm assuming for simplicity also that gamma p is 1. Gamma t, sorry, is 1. Yeah, thanks. Yeah, it's not in general, of course. Okay, so we have this pullback and the canonical bundle formula, and then there is something I will not prove, but I will let me state as slogan. So the slogan is that the restricted fibration is more singular than the fibration we start with. So, of course, this sentence has to be proved, but this implies that the discriminant of the restriction of the fibration is bigger or equal than the restriction of the discriminant. Oops. But then we have the opposite inequality for the moduli parts. Okay, but now, how did we choose T? T is a component of the B plus of the fibration. So this one is numerically 0. And T is a curve, so this one is Nef. So these two properties with the inequality imply that NT equals MC restricted to T. And maybe it's still on the blackboard. Yes, so up there, you can see that the conjecture has been proved if the dimension of the base is 1. So this guy is semiample. Because this one is. And so this concludes the proof of this baby case. So of course, in general, all the hypotheses I've made are not true. And so one has to, for instance, the suitable multiple of xt here if gamma t is different than 1 in order to obtain everywhere is C pairs. And if this guy is not smooth, so there is a subadjunction argument. And also this very vague sentence has to be proved with an MMP technique, which we changed it a little bit, but it's very much inspired by a paper of Fujino and Gongyo. And we'll stop here. Thank you for your attention.